Okay, LeetCode. Every day, June 19, another day, another dollop of misery. I'm wearing my cow shirt, just a little bit of drip. I did valid anagram yesterday, but I got stuck, so I'll probably do it again, only if we finish the regular problems, but I'm just gonna jump into it. Okay, we got some problems due today. I have implement stir. Actually, let me do countdown. Implement stir. The last time I did this was almost a month ago. The goal is linear time, constant space. Set up some key bindings with a function stir with haystack, which is a string, and needle, which is a string, and we're returning a number. So 2 strings and a number. Implement stir. Given 2 strings, needle and haystack, return the index of the first occurrence of needle and haystack. Or -1 if needle is not part of haystack, which we return if needle is an empty string. For this problem, return 0 when needle is an empty string. So if needle length equals 0, then we'll return 0. So it looks like we just have to find needle in haystack and return the index of the first occurrence of needle in haystack. So I think we could just do a for loop over haystack on each index, and then on each index we'll do a substring for where we are to needle's length, and if it matches needle, then we'll return the index. If we make it to the end outside of the for loop, we'll return -1. Do I equals 0, I is less than haystack.length, I plus, and do haystack dot substring starting from index I and going to needle dot length, and if it is equal to needle, then we'll return I. So for this problem, haystack HELLO, needle is LL. Needle isn't empty, so we return 0, and then we iterate from 0 to haystack.length, and then we check starting from index I, which is 0, going to needle.length, or 2 characters from I think is what substr gives us, or it might be substring. One of them is a range, like give me the indices from 0 to n, and one of them is starting at index 0, give me n characters. It's either substring or substr. So we have I needle.length equals needle. LL does not equal HE, so we go to the next iteration. EL does not equal LL. Then we go to L. LL does equal LL, so we return I. Otherwise, we return -1. So I think we should be good, unless this is the wrong function. So it looks like we're fine. So it looks good. That'll be linear time with constant space because we're just iterating over the input string. Actually, would it be linear time if on each iteration? Yeah, I think it would be linear time. With something about the substring. Maybe, yeah, maybe it's fine. So longest common prefix. Goal is O of S, where S is the sum of all characters. O of S, so it's just all input characters into the string. And the space goal is constant space. So the function longest common prefix with strings, we have an array of strings and we're outputting a string. So write a function to find the longest common prefix amongst an array of strings. Longest common prefix. If there is no prefix, return an empty string. Prefix return an empty string. So we have strings flower, and flight. The longest prefix is FL. So I think there is a mathematical way to define this. If we define LCP as a function of longest common prefix, we have string, let's just say string 1, and we have string, actually we have string I, and then we have string I plus 1. It's kind of recursive in the sense that the longest common prefix of 3 strings going up to I plus 2. This has this kind of recursive nature where it would also be the LCP of I and I plus 1, and the LCP of that output plus I plus 2, all the way up to however many we would go to I plus n. That being the case, basically saying that our solution, part of our solution exists as a portion of every element in the array. That being said, we can start this, we can assume, right? The answer is, since the solution exists as a part of every element in the array, we can assume the first element in the array as our solution and then change that as we go through the string. So we'll do string sub 0 equals first string, or actually we can just call it, we'll just assume the longest common prefix is the first string in the array. And we can iterate over every string in the array. So I is less than strings.length, I plus plus, and then we can have a secondary loop within. So we're going to iterate over every string in the array, and for every string, what we're going to do is make sure that before we go on to the next string, we have the longest common prefix so far. And since this function is recursive, or the solution is recursive in nature, once we validate the first string and go on to the next string, it's kind of pre-validated for the previous problems as well. So to explain that, if we start with flower, right, and then we have flow, right, the longest common prefix they share is FL, and that can't, that pre-checks or clears every element after that. It clears them to technically always match until we remove those number of characters. So once you go to flight, we'll still have FL, right? And if, let's just say if this was fight and it lacked the L, then even if we remove an L from the character, it doesn't disqualify the first element and keep the second element, because it's the longest common prefix. So if we remove one character, it still validates the elements we already validated, if that makes sense. So we do while we don't have the longest common prefix, so the only way we can know that is if LCP, right, isn't empty, right? Because if we have something like dog, race car, and car, once we get to dog and race car, they share no longest common prefix. So actually this makes more sense when I explain what we'll do, but if we have dog and race car, what we'll do is we'll compare dog to race car, and we'll remove a character from, let's just say, LCP, which is currently dog, and then we'll check it against race car again, right? Do we share longest common prefix? They don't, right? And then we would keep removing characters off of the end of LCP and checking it against the new length of race car. So for example, if we have character dog, right, where do we start checking from? The end or the front? Well, we're looking for the longest common prefix, so we're going to check from the front. Well, if we start from dog, we're going to check dog against rack. Well, they share no common prefix, so we're going to pop a character off dog, and we're going to have DO. And then we're going to check DO against RA, not RAC. They still don't match, so we're going to pop a character off dog. Again, we're going to have D. Is D longest common prefix of R? It's not, so we're going to pop a character, and LCP is going to be empty. So we're going to need this case LCP.length doesn't equal 0. And then here we want to do that secondary piece of logic we mentioned. We want to check if LCP, right? Oh yeah, I mean, this is the opposite because we want this loop to keep going. While LCP does not equal the strings sub I, so the string that we're currently at, right, dot substring starting from 0 going to LCP.length, right? So if LCP is DOG and string sub I is race car, does LCP, which is dog, equal string sub I, which is race car, substring starting from the 0th index going to plus LCP.length, which is going to be 3 characters. So does dog equal rack? It does not. And so what we would do there is we would say LCP equals LCP dot slice. I think you can say -1, which would take one character off the end, but we can change that. I think there's a shorthand where it would take one character off with -1. And we should be good there. And since we're returning a string, we can just return LCP, which is going to be our output. So if we run this for flower, and flight real quick, you can also optimize this by setting I equal to 1, since we're assuming LCP is sub 0. But it's simpler if there's only one element in the array. This also works. I equals 0, so LCP is going to be equal to flower, and I sub 0 is going to be to flower. Well, LCP.length is not 0, and LCP, which is flower, does equal flower, right? So we're going to skip pretty much, yeah, we're actually just going to skip this while loop because LCP does equal flower. And then we're going to go now string sub I equals 0, I plus 1. String sub I is going to be flow. So we're going to say, hey, is LCP length 0? Flower's length is 5, so it's not 0. So does flower equal string sub I, which is flow, dot substring, so substring of 0 to LCP.length, so flower, 5 characters going to flow. This protects you from going out of bounds. So if I do the substring of, let's just say, cat, and I say give me the character from 0 to the 5th character, it's just going to return cat and not throw an error. So does flower equal flow? It does not. So we're going to remove one character from flower. We're going to have flowy. Is LCP empty? It's not. So does LCP does flowy equal flow? It does not. We're going to pop a character off of flowy. Now it's going to say flow. Well, LCP isn't empty, and flow does equal flow. So we're going to stop and go to the next character, next string, which is flight. And then we're going to say, well, is flow empty? It's not. Is flow equal to flight? It's not. I mean, what's going to say is flow equal to flig, because we're going from 0 to LCP.length, right? It's not equal to flig. So we're going to pop a character off flow. We're going to have FLO. So flow isn't empty, FLO, not FLOW, and it does not equal to fly, right? Because we're going to 0 to LCP.length, and flow, which is FLO is not equal to FLI. Pop a character off flow, we're going to have FL. FL is not empty, and as FL, right? FL equal FL. So we're going to 0 to LCP.length. It does. So this loop ends, and we're at the end of the array here. We return LCP, which is going to be FL. So this should be good. Uh-oh. I think it might be running out of time, so I think LCP.slice isn't probably what we want. Maybe it's LCP. I really thought it was LCP.slice. Might be LCP. I know it's this part of the problem because time limit exceeded, which means the loop is not ending, which means the only place this can't end is the while loop. Maybe it's LCP.slice going from 0 to -1. Or, you know, just to make it even safer, we can just do LCP.length -1. So that works. I'm wondering if you can just do LCP.length to going from 0 to -1. Okay, so there's something about -1, which is not the shorthand that I thought it was, but so this looks good. And time complexity is O of S. The reason it's O of S is because we're iterating through all the strings in the array, But for every string, we're gonna almost, in the worst case, have to iterate over every character in the string. Actually, no. I don't know if an arbitrarily large input could be defined such that it would actually be the sum of all characters in the string. So if we had a really long number of sequences for every string, like something like this, if our input string was like arbitrarily long, let's just say it was like a bunch of characters, like 500 characters, on the first string, it would be reduced to the length of the current string, or 0. So maybe it's linear time in the sense, maybe the worst cases. I don't think it's OFS. I think it's the number of characters in the string. So the number of words, total number of strings in the array. So if we had an arbitrarily large string, it would be reduced to the length of the first string. And then from there, if it, or I guess, in the worst case, I guess it would be linear time. Because if we had, it's not because of the case I created, I guess it's because if we had ASD, I think it's because if we had ASD, except it was like 20 times, then we'd have to check every character in the string even though they match. So I guess you could, okay, I see why it's linear time. So, it would still be linear time. It'd be linear time, I think, in the worst case, not OFS. But the solution people say it's OFS, so I'm going to go ahead and say it's OFS as well. In this case, there will be n equals strings with length m, and the algorithm performs s equal m times n character comparisons. The worst case is still. Alright, that's what I was saying. In the best case, there are at most n times min length comparisons, where min length is the length of the shortest string in the array. Interesting. Yeah, actually, I guess it makes sense that it's OFS. I guess it really depends on the cases you're considering. I guess we'll consider the worst case. But that was fine. We pass. So I have convert sorted array to binary search tree. We have the definition for a binary tree node, the class ES6 class syntax. We have 3 properties, val, left, and right, which can be a number, tree node, or null. We have a constructor, which makes all the values optional. They get set to 0, null, unless you passed all the values in. You have a function, which is an array of numbers, and we have to return a binary tree. Given an integer array nums, where the elements are sorted in ascending order, converted to a height-balanced binary tree. Height-balanced binary tree is a binary tree in which the depth of the 2 subtrees, two subtrees of every node never differs by more than 1. Interesting. So we're given input -10, -3, so it's sorted in ascending order like they mentioned, and they want us to output it in. They want us to output it in a binary search tree, but it's height balanced as well. So I think the height balance requirement just means in the binary search we choose the sender as the pivot rather than a random one. It's also important to note that depth first, in order traversal of a depth first search produces an array in-order traversal, depth for, I guess a depth in-order traversal implies depth for search, but in-order traversal of a binary search tree produces an array in ascending order. Since the array is already in ascending order, we're just converting an array to a binary search tree, or an array to a binary tree. So binary. So we could define a function helper, and this is just going to be the recursive function that is going to handle this, but in a binary search. The method is going to basically do a binary recursive in-order traversal and producing a binary tree from an array. So it's going to look similar to a binary search implementation on an array. So we pass in going from index 0 to nums.length -1, and this would be our range. Right, we're also going to have to pass in the nums so we can actually access the array. So we're going to pass in, so 0 and nums.length -1 are going to be left and right respectively. Oh yeah, which is going to be an array of numbers, and it's going to return a tree node or null. So we're converting an array to a binary search tree, but the array is already sorted. So we just have to transform the array into a binary tree using in-order traversal, which should give us the proper answer. So if left is equal to right, then we're going to do this in-order traversal, right? And if left is not less than or equal to right, it means we don't actually have a valid range to actually choose an element from. So we'd return null. But if it is, then we want to calculate our pivot or our midpoint, which is going to be left plus math.floor of right minus left over 2, and this is just math.floor since JavaScript doesn't have an integer data type. So if we do right minus left over 2, we get a floating point value. We can't actually index the array with it. But also the math.floor also gives us a solution which favors a left-leaning pivot. So we're trying to choose the middle element at all times, but if we have an array like 1, 2, 3, 4, 5, or 6, when we calculate our middle point, it's going to give us 3. When we have the range 1 to 2, which midpoint do we choose? And so if we actually run this in our head, if our left range is 0 and our right range is index 1, well, right minus left, right is 1 and left is 0. 1 minus 0 is 1 over 2 is 0.5 plus left, which is 1. Which is plus left, which is 0, which is 0.5. Right? But if you do math.floor, we actually end up choosing index 0 as our midpoint. But if you do math.ceil, you can actually choose a right-leaning center point. And so both of these can give us different answers. So it's kind of arbitrary which one you would choose. But it's just important to note that the in-order traversal actually doesn't produce a unique solution because of this choice between choosing a left or right leaning. But once we have the pivot, we can create a node. It's going to be a new tree node, and it's going to actually get the value of nums sub pivot, starting our by creating a node, right? And because we want to do an L and R, although we're not actually going to be calling any of recursive function for the end portion, it's kind of a little bit irrelevant. But if we were calling a function, it would be closer to like in-order traversal, because we're just kind of choosing a value for pivot. and you kind of need the value before you can do node.left, it's going to look like preorder, because we're actually going to do node, right, take the value of the node, then figure out the left tree, then figure out the right subtree. So it looks like preorder, but just because you can't do something like this. So then we call helper again with a new range, and the new range has to be exclusive of the pivot, since the pivot is what we already created a value for on line 18. So we're going to go from left, right, to pivot -1, and we're going to pass in nums. And just duplicate this line, change it to right, and for this one we're going to go from pivot +1 to right, and we want to make sure to return the node. So I think this should work. We should run it in our heads just to make sure. So they give us the array -10, -3, 0, 5, and 9 to convert it to a height balanced binary search tree. We're going from the range in the array of 0 to nums.length -1. So we have 5 elements in the array. And actually, let's change the one we're running to a small array just so it's easier to imagine. And we'll just take away. We'll take away 2 of these elements, so 10 and 5. So it'll be a short run. So the range we're going to go to is going to be from 0 to nums.length, which is 3 -1. So 2 is going to be the last element in the array that has a value. So 0 to 2. 0 is less than right. We're going to calculate our pivot. We're going to do right minus left. And actually, let's just choose floor, so we actually get this answer here. And they say this is also accepted, so we can actually change this to seal. So this is our similar what we would get. Actually, no, because we chose different elements. So let's just choose floor. And so we have math dot. So you have 0 to 2, right is 2, and left is 0. So 2 minus 0 is 2, over 2 is 1. Plus left, which is 0, so you have index 1. Index 1 is going to be our center point. So we're going to create a new node. We're going to put 0, num sub pivot, which is index 1, which is source 0, a little confusing, into this array. Into this binary tree. And then we're going to have this one element node, which is going to be right here. Then we're going to have node.left equals helper left. Left is 0, going to pivot -1. Well, pivot was 1, so pivot -1 is going to be 0, right? So we're going to be in a new recursive function. We're going to start over. We have 0 and 0 as our left and right values. Well, left is equal to right, which is also 0. So our pivot is going to be 0 minus 0, which is 0, over 2, which is 0, floored, which is 0, plus 0, which is 0. So we're going to create a new node with num sub pivot sub 0. This is going to be -3 because the number at index 0 is -3. And we're saying create a new tree node with num sub pivot sub index 0, which is -3. So we're going to have -3. Now we're going to calculate the left subtree for -3. So left is 0 and pivot is also 0. So pivot -1 is going to be -1. Passing in nums. We're going to go back to the top with 0 and -1. 0 is not less than or equal to -1. We're going to return null for this node right here. We're going to go for the right node of -3 now. So pivot +1, and the pivot was 1, going to right, which was 0. So is 1 less than or equal to 0? It's not, so we're going to return null for the right subtree of -3. Well, since we finished the left and right subtrees for -3, we have to go back up to 0 and do the right subtree for index 0. So our pivot here, when we first called the function, was 0 and nums.length -1, so 0 and 2, right? And our pivot we calculated was index 1. So pivot +1, which is 2, going to right, a pivot +1, which was 2, and our right index was 2. So 2 is equal to 2. Calculate our pivot. Right minus left is 0 because they're both 2. Divided by 2 is 0. Plus left, which is 2. So we create a new tree node with num sub index 2. What's at index 2? It's 9. So we create a new tree node with index 9. We calculate the left and right subtrees, which are both going to be null because left is 2 and pivot minus 1 is going to be 1, and 2 is not less than 1, returns null. 2 plus 1 is 3, and 3 is not less than or equal to 1. We return null, we return the node. So I think this should be good. So that looks good. And I think the time complexity of this is actually going to be linear time since we visit every element in the array. So it's going to be dependent on the number of elements in the array. But space complexity, I think, is going to be log of n. And why is it log of n? I think it's log of n because to create nodes for n elements, we need n over 2 calls. N over 2 calls to helper. No, but if we're visiting every element in the array, let me check the solution. This is O of n, since we visit each node exactly once. Space complexity is log of n, because this tree is high balanced. Tree is high balanced, which means we choose the center as the pivot on each iteration. I don't understand why the recursion, because the tree is high balanced, makes the space complexity log of n. Maybe we'll figure it out in a future binary tree problem. So we have min stack as well. Oops, try not to look. So design a stack that supports push, pop, top, and retrieving the minimum element in constant time. I see, implement the min stack class. Okay, so push, pop, and top you get for free, being constant time in an array, with the underlying data structure being an array, and retrieving the minimum element in constant time. That is where this magic has to happen. So push takes one parameter, which is a value, pushes the element value onto the stack. Pop moves an element on top of the stack. Top gets the top element on the stack, and get min retrieves the minimum element in the stack. Minimum element in the stack. Makes sense. Pop, top, and get min operations will always be called on non-empty stacks, so we don't have to check if they're empty before doing a lot of operations, but I think it's good practice to do so. So I think last time we did this with 2 parallel arrays, but this time let's try and fuse it into one. So we'll have an array of tuples, and the first element is going to be the actual minimum element, the actual element in the stack at that position. And the second element is going to be this minimum element at the time of adding that element onto the stack. We have 1, 1, right? They want us to add another element, which is going to be 0. The next tuple will have 0, which is the actual element at the stack, in the stack at that time. And the second element in the tuple is going to be the smallest element so far, which is 0. So we're going to see that the smallest element so far is always a function of the last smallest element so far, and the element being added into the into the stack. So if we do like, if they want to add 5 to the stack, we'd add 5 to the stack, right? And the smallest between adding 5 to the stack and the smallest element we just added, which is 0, be 0. And so we can always get the smallest element in constant time, since we always have track of the smallest element that we added. So we'll do min. I made this mistake last time. Class syntax. We're going to have min stack equals an empty array. We can just delete the constructor. We'll check if this dot min stack dot length so we're going to want to push this element onto the min stack. I think I'm going a little too fast. So we can push this element onto the min stack, but we actually have an array of tuples that we want to work with. We have to figure out the smallest value. So we'll say let the smallest value so far just be equal to and so we have to get this special value. The smallest value so far has to be the minimum of the value we're adding and the last smallest element in this array of tuples. We also have to have handle an edge case that they said doesn't exist. Those will always be called the non-empty stacks. But yeah, I think it's good practice to handle anyway. So what's the best way to do it? We could do math.min, right, of val, and this dot min stack. So this dot min stack dot length -1. But this doesn't handle when we have the last index in the array. I mean, when there's no elements in the stack. So I think we can just do this with a ternary operator. So say this dot min stack dot length equals 0, then the value that we'll return is going to be infinity. Otherwise, we're going to take the math.min of the value we're adding to the stack and the smallest element we've seen so far. So that would be val, and this sub min stack.length -1, and the second element in the tuple. Then you can push that onto the stack. We do pop, we'll just do this dot min stack dot pop. I think arrays in JavaScript don't throw an array when you pop an empty element off an array. But I guess we'll see. And to get top, if this dot length, this dot min stack dot length equals 0, we'll return -1. Otherwise, we'll return this. We'll return this dot min stack sub this dot min stack dot length -1 sub 0 to get the actual smallest, the actual value on top of the stack. And then we can actually copy this one for get min. If the stack is empty, we'll return -1 as the minimum. Or maybe we could do -infinity. And if the stack isn't empty, we want to turn this sub min stack dot length -1. So the smallest element, smallest value so far. Smallest value equal. If the min stack is empty, we're going to return infinity. We want to actually return positive infinity. Actually, no, negative infinity. Otherwise, we return a math.min with the value we're pushing onto this stack, and last element in the min stack tuple, first or the second element at index 1, which would be the smallest value so far. I think this should be good. So the two things they run at the end is push, get min, which is -3, so we're good there. We do a pop, return null, we get the top, which is 0, and then we get min. It's not the right value. I think that means that math.min value and this.min stack, so this.min stack dot length -1. Okay, I see the problem. I actually don't know if this shorthand is possible. We do. Let's do smallest value. We're gonna assume it's gonna be val, and then we're gonna push this min stack and smallest value. Now, if this dot min stack dot length is not equal 0, and this dot min stack sub this dot min stack dot length -1. So the smallest element so far is smaller than value, and we set smallest value equal to this dot min stacks this dot stack dot length -1 sub the smallest value. I think this one should actually work. My keyboard doesn't support, I think it's N key rollover, so I make a lot of typos. So that one works. The reason the other one didn't work is because when the array is empty, the element that we add on to the stack, we want it to be the small. So if the array is empty, the underlying data structure, which is the min stack, is empty. When we add 5 on, if we push 5 on, the tuple should say 5, 5. But what was happening before is that the tuple would say 5, and I think it was infinity or whatever I set it to. I could have changed that to not be on with the tuple, but the whole reason that was a problem is because I used a ternary operator. So that looks good. And pop, top, and push you get for free in constant time just because of the nature of arrays. And get min is why push is a little thicker. But at the same time, the tuple version of this solution is a bit convoluted, so I think the parallel array version is better. We didn't get to do these other ones. You can like valid anagram, but we'll try valid anagram tomorrow. But yes.